Hi everyone, my name is Sharjil Ali and I'll be presenting my paper for Comp 5115. So as for some background, the paper I'll be presenting is called the Field Guided Registration for Future Conforming Shape Composition and published by these authors over here. So in general, the topic behind this paper is related to the problems with alignment and stitching of two different meshes together. So as for some introduction, why exactly would you try to align and stitch meshes with holes together? Well, the whole point about this is to more efficiently create new shapes. So instead of spending some time creating shapes manually by hand, you would take existing shapes and then combine them together to create new shapes, which is an effective way to increase dataset sizes. However, the issue with this is that part composition in general is not really well studied. So there's that, which is then related to the two major issues with part composition being how to automatically line these shapes together. So for example, given these two parts over here, how would you take them such that they align like this? And then how would you fill in the gap between them and stitch the two surfaces together? So in more particular sense, the problems related to the alignment section is that it's related to the idea about overlapping. So essentially, previous papers before this one, they only really work when trying to align together parts that are overlapping. So for example, this would be an Icp algorithm that we learned in class. So given these two shapes, they would align together, but they're pretty similar, and they're overlapping in terms of their shape similarity. So then it's harder to overlap or to align meshes that aren't overlapping, essentially, with unique parts. And the other issue is that when aligning, it ignores sharp features. So these sharp features might tend to get blurred together, essentially. So it doesn't really preserve these sharp features. As a result, the best method is still trying to manually align meshes to if they don't have overlapping parts. So this paper introduces a solution for this issue with overlapping by essentially creating a method to implicitly extend the surface from the holes. And then from there, it would extend in such a way such that it creates sort of an implicit overlap between the two parts. And then this overlap can then be used to align the two meshes together. So this is done by computing in a future conforming field called an FCF, which is an implicit function that can then be used to transform, and it's similar to the RBF method that we learned in class. So for example, in this diagram, given a mesh P and a mesh Q, you can see that its implicit surface, it extends downward over here and also over here, but when aligning these methods, you would align this such that these two implicit extensions are similar together, aligned properly, which creates this new stitched aligned method over here. And you can see that the implicit surface is pretty well aligned. So the main idea behind this is to check if a transformation that's being applied to a part, checking to see if this part lies on the other part's surface. So for example, this will then require an implicit function to check both the orientation and the distance. So given an example, let's say you have a point over here with a normal facing upwards and a circle implicit function with normals colored in red. If you were to apply transformation t, you would then check, okay, does the point lie on the surface of this circle? Yes. And then does the normal direction, is it matching? Yes, it is. So then this is a good transformation to use to align both of the meshes. And as for the issues with stitching, is that they only really work on smooth and not really sharp features. So as a result, for example, in this case, let's say you have a mesh like this. Previously, when stitching together the surfaces, this would be a pretty simple problem. However, if it has edges like this, the issue is that how would you stitch together the meshes such that they preserve the sharp edge features, like the yellow lines over here. So this is done using something called Spline Interpolation, which it essentially creates this texture. So basically for each part, so let's say for a part P and a part Q, it would then match up the edges together, and then these would be used for the basis for a piecewise smooth surface reconstruction between the two geometries. As well, the paper has two contributions. The first is creating the field-guided registration algorithm, and then a future-conforming shape composition, which ensures edges are kept between the two shapes. So the paper mentions over 20 related papers, so not all of these will be covered, obviously, but a few that I found interesting with. So for example, starting off with this one, the Icp Snapping Method over here. So in this case, the user would manually specify which parts to overlap, such as the head over here or the two claws. And then afterwards, the Icp method would then it would beautifully merge local points over here. So it would then take these points, it would apply the transformation locally instead of globally, like we learned in class. So this means that like as a result, it would be deformed and blended together with the surface compared to a regular ICP method over here. However, once again, like this, it doesn't really work for non-overlapping parts. So this is a limitation of this paper. And then this is another idea is partial matching methods. So in this case, parts need overlap to be aligned. So essentially the whole idea about this is that you select parts that are overlapping, for example, the two faces of the people, their hands or their feet, and then you would align based off of those features. So for example, given two people, you would align based off of the head versus just aligning normally. But once again, this requires overlap, which is a big limitation. Another one is stitching together similar shapes. In this case, you would identify common features called classes between meshes. For example, you would identify the heads of these different animals, their torso, their legs, and then you would only stitch together these parts, which would ensure a good compatibility between shapes. But once again, it's limited, right? You can't really stitch together different parts. You can't stitch a foot to a head, for example. And another one, in terms of the actual implicit field methods that the paper uses, I'd mentioned it does some comparisons to the RBF method. And to tensor voting, which essentially chooses the best likely point or the best likely value if a point exists on the surface. So for example, if when aligning using the RBF method over here, two parts, it's pretty smooth, but the actual alignment can be seen it's pretty bad. Same thing for TV, but the FCF one, it preserves the sharp features over here, as can be seen. So it conforms to the sharpness compared to the other two RBF and TV methods, which smooth out the shape. So then the methodology is split up into two different parts. The first part is the field-guided registration, and the second one is stitching of the gaps. So I'll talk about the first part first. So registration is then split up further into two steps. The first is for each part, P and Q, you would create the FCF that would use to be checking if a point lies on the surface extension. So basically, it's a scale of saying, okay, how likely is it that this point exists on the surface? And then this would require a distance calculation and a direction calculation as well. And afterwards, you would then solve for a transformation that would align both parts using the FCF. So the first question is, well, which points would you use for the FCF? In this case, you don't need to select all the vertices of the mesh. So in this case, the red area would represent the vertices you would use near the whole boundary. And this is because of two reasons. The first reason is that the vertices that are being used, they would define the implicit extension shape. So as you can see, it's extending upwards, like similarly in the direction that the neck is facing. However, if you use other vertices outside, like the arm, for example, it might cause some noise to this calculation over here. And that's why, and you can store this in omega subscript p. So then the next issue is exactly, so why would we require computing the direction? That's because when aligning translation and rotation are important to align both meshes together. And then the direction that you would try to compute would be essentially the direction of the maximum likelihood that the point exists. So for example, given this diagram, as you can see, there are two. For example, there is this blue direction and this red direction. This blue direction yields a sort of red circle, which would be the likelihood, and this red one yields an even bigger circle. And then you would find the direction that has the bigger circle. And these circles represent basically the scalar values of the maximum likelihoods. Whichever direction yields the maximum likelihood, you would return. And then in terms of assumptions, you can assume that that the best direction matches is similar to the direction of the surface normals. So for example, as you can see, these three normals, they're similar to this red one compared to this blue one. So that means that the red one is more likely to be the correct one. So then how would you actually compute this maximum likelihood? You would compute d subscript p of s, which is this function. It's essentially a summation problem where you would where for each point in the selected vertices omega of p, you would compute a phi1 and a phi2 function, and then from here you would optimize for the maximum value d in dp of s. Essentially, what this means is that given a point s and a list of vertices of omega of p, you would find whichever direction returns the maximum value from this function. And in particular, to solve the first Gaussian function, phi1, what this means, this is essentially, it's saying to essentially select whichever point is nearest to the side. So the more particular what this means, for example, you can see that s minus u over s minus over the magnitude of s minus u. This is the distance from a point s to a vertex u on the surface. So essentially, what this means is that the maximum likelihood would be returned for a point that's corresponding to the side. So for example, s over here, this point is more close to this point versus this point all the way over here. So as you can see, this is unlikely because it's too far away and it's on the opposite side of this surface area. So that's why this point s over here is more likely. Then the next one is the second Gaussian, which is phi2. And this one works similarly, except now it's selecting, it will return higher values for directions that are similar to the normals u. So for example, given the normal u over here, as you can see, it's similar to this red direction compared to this blue direction. That means this red direction arrow at the bottom, this is the more correct or the more likely direction. And as a quick recap, here are the three equations that are being used. So afterwards, the next issue is how would you compute the distance from S to the surface extension? So this requires computing a function L of P of S, which is, it uses the direction calculation from earlier on, as well as a new phi function, so phi3. And then exactly what is phi3? Phi3 is basically, it's used to measure the distance between a point S and a point U on the surface. And then, as we all know, the way implicit functions work, the closer a point is to the surface, the value starts to decrease. This means that the likelihood of a point existing starts to increase then, which can be seen in this diagram over here. So as a quick recap, here are the equations for the distance calculation. So the next issue is how would you compute the likelihood that S actually lies on the surface extension using both of these directions and distance equations. So this is done by computing K of P of S. Now the K of P of S is essentially this equation over here, and it's pretty simple. So the whole point about this is that normals of the point S that are matching, that are in a similar direction to the direction d subscript P of S, which is what it should be on the actual surface. These would return a high value, and the same thing for distance. A lower distance, that means it maximizes the likelihood that the point S lies on the surface. And that's pretty much it for computing the FCF, actually. So afterwards, next issue is how would you compute the best transformation that would align both of these parts together on the surface. So this is done by function EFT. And the whole idea about EFT is that for each vertex in both parts, so part P and part Q, you would then check if a transformation that's being applied to them would align it onto the other part's surface. So for example, for part P, you would take part P's vertices, transform them by T, and check if these align onto the FCF of the other part of part Q. And then you repeat this, but instead you use the inverse of T. So instead for part Q, you would check for each vertex in part Q, does the inverse transformation align it to the implicit function of part P, sorry. And this means that it can work both ways. So it ensures that you can align them, that the order doesn't matter. You can align them both ways. And in this case, this would return a likelihood value that they're both aligned together properly. And in this case, you would find the best likelihood, so the best EFT value. That would mean that the transformation T is the best one to use. So for example, this is for example how it's being aligned. So given FP and FQ, as you can see, like the implicit directions over here, once they're aligned properly, the implicit surfaces, they're being aligned pretty well. That means it's a good transformation. So now the next issue is how do you actually compute this specific transformation? So in this case, it's similar to computing the direction. You would try to optimize the maximum T parameter in EFT, and then they specify using a BFGS algorithm. So this requires first an initial value for T to be used, and from this initial value, you would then iteratively find the local maximum of the EFT. So now the next question is exactly, well, how would you find this initial value of T to use? So the thing about trying to find the initial value of T is that if you find an incorrect value or like a not so good value of t to use as the initial one, it might lead to the incorrect transformation because the BFGS only finds local maximums, not global ones. In this case, you would use like a random search one method in which you would randomly sample, let's say, 10,000 transformations of t, and then you would then select the transformation that would yield the highest value of BFT, and use this for the initial transformation to be used in the BFGS algorithm. And that's pretty much it for the registration component. And then as for stitching now, so stitching is split up into 3 steps again. So the first step of stitching essentially involves computing the salient curve structure, which will be discussed soon. So essentially you would compute an inside the structure in which that would preserve the sharp edges between the 2 parts. And then using these edges, you would then, using each of these sides in the structure, you would then use the line triangulation to then fill these sides in 2D, which would then fill up the gap between both of the parts. And then once this gap is then filled up, the issue now is that the line triangulation, it results in a 2D vertex, but you want to translate this 2D vertex into 3D. So you would solve a linear least squares method, which would then return the final coordinates of both of the gap between both parts, and which would then lead to a good transformation or lead to a good stitching method. So the first question is, how would you find these sharp edges on the whole boundary? So you would select all the edges with dihedral angles less than 65 degrees. So a dihedral angle in this diagram, as can be seen, let's say you have an edge over here, and you have an angle inside the mesh, so with phases beta and alpha. If the angle inside is less than 65 degrees, then that means this is a sharp edge. And then you would first off denote the sharp edges along the holes as seed vertices, so UP and UQ, shown in red colors, so these ones over here. And then from these seed vertices, you would then compute salient curves. So in this case, salient curve would just be the sharp edges that are being traced backwards along these seed vertices, which would be stored in CP and CQ. So for example, given the seed vertices in red, you would then start tracing backwards away from the hole. And then when to actually stop tracing, so then you would stop tracing these salient curves for 2 reasons. The first is when a sharp edge no longer exists. So for example, given this mesh, you can see the yellow represents the sharp edges. So as you're moving backwards, the angle, the sharpness, it becomes much more flatter, which can be seen by the red arrows. And then eventually it will reach a point in which there's no longer a sharp edge, which means that you can stop tracing. And second case is, as you're tracing over here, you might encounter a bifurcation, which means that that the edge splits off into 2, and you can't reasonably guess which of these 2 is the sharp edge to use. And so in this case, you would stop as well. And once you have both of these curves, you would then create a corresponding match, for example, from part P to its corresponding match in part Q. And then what this means is, for example, so this would result in a line I of j. I would be a point. I would be the curve in the salient curve in P. J would be the salient curve in Q. And then, as mentioned over here, so in this case, you would then use the FCF algorithm to then find the greatest likelihood match between them. And then you would solve for j this equation over here. So what this, for example, means is that given a curve P at I over here, you would then find the best possible corresponding match in Q. So out of these 3 j values, which of these would result in the best one? And that one would be this one right over here, which would then result in a corresponding match I of j between the curves, which would then be stored, in which both of these 2 curves, so CPI, CQJ, would then be stored in Cij, which represents a cubic spline between both parts. And a cubic spline, if you're wondering, it's just essentially a curve formed out of points. And this is what it would look like. For example, for one curve right over here, you would have a corresponding line, so a cubic spline between both parts P and both parts Q, which would then form a sided structure. So you can see this side has 4 sides, 1, 2, 3, 4 over here. And then from, yeah, right over here. And then from these, you would then create a 2D rectangle out of the gap. So from each side, you would translate this into a 2D rectangle. And then you would use constrained Delaunay triangulation on each of these sides, essentially. So so a quick recap of the Delaunay triangulation. So for example, for a number of points, you would create a circle around each point. However, the constraint is that no circle lies inside the circumcenter of a triangle. So what this means is, as you can see, basically each point on a triangle lies on a circle. And this is essentially how you compute the Delaunay triangulation. However, constrained Delaunay triangulation is similar, except now you force these triangles that are being formed onto defined edges. So in this case, the defined edges would be the boundaries between both parts, which would then form a structure like this, which then constrains the triangulation onto a rectangle. And from here, the last step is because Delaunay triangulation is done in 2D, you want to convert these 2D coordinates into 3D, which would then result in 3 different vertices. So currently, you would have the surface vertices, the curved vertices, and the gap vertices. And then you would store all 3 vertices into a set of I. You would then store the vertex connectivity of all the gap vertices in G, and then the final coordinates would then be stored in the set of X, which then needs to be solved. So you would solve for X leading to the final coordinates of the stitching. And then you also have the control group Y. So the control group just includes basically both the surface and curved vertices and not the gap vertices, because remember, we're trying to solve for the gap vertices, not the surface and curved vertices, which we already know their coordinates. So to solve exactly what the coordinates are in the set of X, you would use a least squares algorithm. So what is the least squares exactly? So as a quick recap of least squares, it's essentially trying to minimize, trying to find the line of best fit between a set of data. So in this case, when it's saying minimizing X, it means minimizing the error between what it should be, for example, the line, and what the points actually are. And in this case, what L over here would represent, L would represent the Laplacian operator, which then is constrained using the values of G being the vertex connectivities. And from here, so next issue is what the weight term would be used for. So right over here, as you can see, there's a weight term W. So this weight term is actually used for computing the deformation for both for the vertices on the surface. However, so basically a higher weight would then result in a larger deformation being applied. And why do you need to deform a shape? That's because sometimes you might not be able to create a good continuous stitching between them. So you need to deform them to make the stitching between them smooth. However, this weight is different for both curve and seed vertices. So as for the surface weights, essentially, the surface weights would be the one, so these are essentially the weights that are not on the curves, essentially. So this one, you would compute it using this equation right over here. And then exactly what R is. So R would be the Euclidean distance between a point Y on the surface and a centroid of the gap. So centroid is essentially the mean average of all points on the gap. So for example, given a point, so the centroid in this case would be in the middle between the two gaps using the seed vertices or the vertices along the edge. You would then create the centroid. And then this other part, so there's R hat part. So this actually wasn't explained too well in the paper, so I had to guess what this means. But essentially what I guessed is that the centroid in this case would essentially be the centroid of all the Euclidean distances between the two parts. And then this would deform apart. So essentially the closer Y is to the edge, the more deformed it will become. However, for the curved vertices, because these define the edges, if you remember, these do not need to be transformed at all, because then it would result in the sharp features not being preserved well. So in this case, assign a constant weight to them. So that was pretty much it for the actual implementation and the method. So in terms of the actual results, so as can be seen for man-made shapes, the results are pretty well done. So as you can see, it creates the gap in yellow between them. And even if the salient curves don't match, so for example, this shape has quite a few edges, well, this one doesn't, it will still find the best match and then slowly over time smoothen out the edge. And then for multiple parts, it also works when you're stitching together multiple parts, for example. So given this mesh over here and this down, you can see it can stitch together when there's two holes. So there's that part as well. As well as overlapping parts. So I found this part quite interesting. So for overlapping parts, ironically, it doesn't actually stitch together overlapping parts quite well. So instead, what the paper represents is a method in which, if there's an overlap, it will then recede the mesh a bit. So meaning it will remove a lot of faces and vertices along the edge, which would then ensure there's a gap between them, which can then be stitched together. And then they also tested it on using sharp features. So in this case, they added some noise to some meshes, and then even with noise, as can be seen, it's still aligned and stitched the meshes pretty well together. So as for the limitations, there are quite a few. So the issue is that you can only align two shapes at a time together. So if you have 3 or more shapes, then it will not work. And then it only considers the area along the boundary when aligning the parts and not the entire shape, which this will be explained in a few seconds why this is an issue. And then it can't handle complex alignment. So for example, given this green knob at the top, you would expect it to be facing upwards or right over here. However, when you align it together using an imperfect hole at the bottom, you can see it doesn't align it properly because of the way that because it only selects the boundaries. It only selects the vertices along the boundaries, so it thinks it's aligned properly like this, even though it should be aligned upwards like this. That's one issue. And another issue is that with aligning using only the boundaries is this issue with directions. So for example, given a human and a horse, you would expect that when these two are aligned together, it would form a centaur like this. However, instead it forms this because this is the more correct geometric alignment instead. So instead, the user can specify the direction the mesh is facing. So for example, this mesh is facing this way, the horse this way, and then it will find the best registration that allows these two directions to match, forming a centaur. So this is essentially one part of the constraint that the paper mentions. So as for my final thoughts on the paper, so in terms of the contributions, I found them quite interesting, and they make sense, and they are quite novel in terms of their methods. I haven't really seen any sort of new methods that use implicit functions really, so I found that to be quite interesting. However, I found that I felt they could have focused a lot more on their novel constraint methods. For example, what I just mentioned about directions and how you can specify the direction the mesh is facing. I felt they could definitely focus a lot more on that. However, the explanations, I found lots of issues with the way the paper explained things. So for example, it did not explain concepts too well. It could just be because of my inexperience about reading the paper, but I found a lot of stuff pretty confusing, such as vague descriptions or missing information. If you recall, when computing when I was talking about the centroid weights, right? I mentioned that I had to make an assumption about what those weights meant, because the paper never really mentioned it at all. And in terms of my project proposal, so as I essentially plan to implement the exact same method that was found in this paper. However, with one new addition being that automatic hole creation. So essentially the paper requires the user to manually create the holes and then use the method to align them together. So my idea is, okay, what if the user can specify a point on the surface, or instead the program will randomly select a point constrained by, for example, low surrounding curvature, and then use that point to create a hole and then stitch them together, essentially making the entire method automatic. And then as a result, my main priority is to complete the registration or stitching due to time constraints. So in case everything else can't be done, I at least want to get the registration done first. And yeah, thank you for your time. And yeah, that's pretty much it. Bye.